Hello, today we are going to take a look at how to calculate some derivatives of some non-polynomial functions. So we have a rational function and a radical function here, as well as take a look at how to use derivatives, both first and second, to calculate critical points, intervals of increase, decrease, and where a function is concave up and concave down. First off, we are going to calculate the derivative of this rational function. F of x is equal to 1 divided by x minus 1. When we are calculating our derivative, the first step looks like all of our other first steps for calculating derivatives. We take our limit as delta x approaches 0 of f of x. Let me just resize this a little. F of x plus delta x minus f of x, all divided by delta x. Now, for rational functions, what we will need to do in order to factor out a delta x so that we can evaluate our limit by substituting 0 in for delta x is find a common denominator in this numerator. There are no common factors between these two denominators in the numerator, so we need to multiply this term by x plus delta x minus 1 and divided by itself, and this term by x minus 1 divided by x minus 1. What ends up happening from there, we still have our limit as delta x approaches 0. Our numerator in the numerator is going to be x minus 1, but since we're subtracting this entire piece, we need to change all of these signs. So it will be minus x minus delta x plus 1. And again, we can check our work with this. If there is a term after we combine like terms that does not have a delta x in it, then we did something wrong and need to double check. Our denominator in the numerator is x minus 1 multiplied by x plus delta x minus 1. We do not need to multiply that all out. That is all still divided by delta x. Then we can combine some like terms. X minus x is 0. Negative 1 plus 1 is 0. And then this delta x moves into the denominator. You can look at it as when you're dividing a fraction by something, that division can still happen as multiplying those two denominators together. It's like if you're doing 12 divided by 3 divided by 4, that's the same as 12 divided by 3 times 4, because you can group that together. Or you can look at it as we've got delta x divided by 1. When you divide by a fraction, you're multiplying by the reciprocal. We still have our limit as delta x approaches 0. And our numerator is negative delta x. Our denominator is delta x times x minus 1 times x plus delta x minus 1. We can now factor out a delta x. And after we have factored out that delta x, which that's a step that we will be doing no matter what type of function we're working with here, then we can evaluate the limit by substituting 0 in for delta x here. Our derivative of f of x then is negative 1 divided by, well, if this delta x is 0, we have x minus 1 times x minus 1, which we can rewrite as x minus 1, the quantity squared. So that is how we calculate derivatives for rational functions. For radical functions, we still want to set this up the same way that we have all the other ones. So g prime of x is equal to our limit as delta x approaches 0 of f of x plus delta x minus f of x, all divided by delta x. It's going to work slightly differently for our radical functions and it's going to involve multiplying by a conjugate. This is something that we've done when dividing by complex numbers or when we are dividing by a square root and are trying to rationalize the denominator. What we need to do instead is multiply both our numerator and denominator by the conjugate of our numerator. So we keep the same terms but change the sign in between. What happens in our numerator is that we multiply conjugates and end up with a difference of perfect squares. So it will be this term squared, which is going to be 4 times x plus delta x. And we're subtracting this term squared, which is 4 times x. Our denominator, we can just leave as delta x times that quantity 2 root x plus delta x plus 2 root x. And we're not ever going to need to multiply that out. Our numerator, then we will distribute that 4, still keep writing our limit as delta x approaches 0. So we've got 4x plus 4 delta x minus 4x divided by delta x times the rest of that denominator. From here, we combine like terms. 4x minus 4x is 0, and we can factor out delta x. After the step where we factor out a delta x, we can always then evaluate our limit by substituting 0 in for delta x. Our numerator then is just going to be 4. Our denominator, since this delta x is 0, so we have 2 root x plus 2 root x is 4 root x, but we can factor out the 4's, and when we factor out the 4's, we are left with our derivative as 1 divided by the square root of x. That is how we calculate the derivatives for any rational or radical function. Next, let's take a look at this function and finding the intervals where f of x is increasing, decreasing, where it's concave up, where it's concave down, and calculating all critical points. We're going to do this in 2 steps. The first one is when we use our first derivative to find our increasing, decreasing intervals and our maximum and minimum values. Then our second step, we will use our second derivative indicated by f double prime of x to find our inflection points and concavity. First thing, let's find our first derivative. F prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus, well, we still have the rest of this, and then minus f of x, all divided by delta x. Every step we need to write that limit as delta x approaches 0. We expand this using Pascal's triangle. And I understand that these can be a little space consuming, but make sure you're being clear with each step and you will be okay. I'm not sure why my pen is not cooperating right now. So this should be a minus x squared minus there we go, minus x squared minus 2x delta x minus delta x squared. I'm just expanding that x plus delta x squared and then also distributing the negative in the same step. And we have minus x cubed plus x squared from our f of x that's here. That's all still divided by delta x. Now, we are going to see a lot of terms cancel out here when they're added to their opposite. So x cubed minus x cubed is 0. Negative x squared plus x squared is 0. And every term in our numerator has a delta x in it still. So what we can do is factor out a delta x. And let's rewrite this because this is getting a little messy. So we have 3x squared plus 3x delta x plus delta x squared minus 2x minus delta x. Okay, not sure what happened there. Now we can evaluate this limit by substituting 0 in for delta x, and we end up with our first derivative to be 3x squared minus 2x. What we do to calculate our possible critical points is set our first derivative equal to 0. To solve this, we factor out an x. We set each of these factors equal to 0 and end up with x equals 0 and x is equal to 2/3. To justify where this function is increasing or decreasing and to also find where our maximum and minimum values are, we justify using a sign chart. We label our number line part of the sign chart with x or whatever variable we're using in our function. And then what we will do is place our zeros of our first derivative on the number line. We will have a row for our first derivative and a row for our original function. In our f prime of x row, this will look very similar to how we found out the values and signs for our sign charts with our polynomial and rational inequalities. F prime of x is equal to 0 when x is equal to 0 and x is equal to 2/3. When calculating whether an interval is positive or negative, we need to substitute a value in. So for example, we substitute in -1. So we're finding f prime of -1. So we've got 3 times -1 squared minus 2 times -1, which is going to be 3 plus 2 is positive. We pick a number between 0 and 2/3. So we'll say 1/2. So we've got f prime of 1/2. And then, so that's 3 times 1/2 squared minus 2 times 1/2. 1/2 squared is 1/4. So 3/4 minus 1 is going to be negative. We pick a value . Okay, so we pick a value that is greater than 2/3, like 1, and f prime of 1 is going to be 1, which is positive. When our first derivative is positive, our function is increasing, which we can show by drawing an upwards arrow or writing increasing or INC. When f prime of x is negative, f of x is decreasing. So when the function goes from increasing to decreasing, that means that x equals 0 is a maximum point. Then, when we look at x equals 2/3 is going to be a minimum point because the function is decreasing before and increasing after that value. Now we can move on to step 2. So we'd write that the function is increasing on the interval -infinity to 0, and then also on that interval from 2/3 to positive infinity, it is decreasing from 0 to 2/3. Now, we can then label where our maximum and minimum values are. We need to move on and calculate the concavity. What we need to do here is find our second derivative. For that, we find the derivative of the derivative. So we're taking our limit as delta x approaches 0 of f of x plus delta x minus f of x